Okay, so as promised earlier, a couple weeks ago, I think when we were talking about, I think it was maybe when we were finishing up RSA encryption, I talked about how in terms of crypto systems, we frequently find ourselves in need of some large prime number, right? So say some prime number that has like 100 or more digits. And so the question I had was like what if you actually needed to find one of these prime numbers, right? And so you didn't have like a handy list of them or anything in front of you. What if you needed to pick a 100 digit prime number on your own? So the point is that even having access to a computer, so I'm not like being super sadistic and making you do this by hand or something, but even having access to a computer, how would you actually check that a given 100 plus digit number is prime? Without having a list that you trusted in front of you, right? Maybe even if you had a list of supposed 100 plus digit prime numbers, maybe you wanted to even check that things on that list were actually prime, right? How would you do it? So one thing is to note, so say you need to come up with, or to verify that a given particular one is prime, but say you need to come up with a prime number having say, the 100 digits. Right? So how do you do this? Okay. So, probabilistically speaking, we have the prime number theorem, which, as I've mentioned it previously, is a very, very powerful theorem, and something the proof of which is beyond the scope of the course. So I've stated it in various forms, but prime number theorem says, among other things, that the chance that a random 100-digit number is prime is like 1 over the natural log of 10 to the 100, basically. So density of primes near a large number x is approximately 1 over the natural log of x. So the chance, so this is what one of the ways you could, it's one of the things prime number theorem tells you. So the chance that a random 100-digit number is prime is like 1 over the natural log of 10 to the 100, which is roughly 1 in 230. Okay. So notice this is the density of primes near large x, so this is the chance that a random 100-digit number is prime. But of course, every other 100-digit integer is even. And we know that even numbers aren't prime unless they're 2. So actually we can do better than this by saying, I don't want to just pick a random 100-digit number. I want to pick one that's odd, clearly. So by considering only odd, so only odd 100-digit numbers, we can get this probability to, roughly 1 in 115. Okay. All right, we're literally cutting the amount of chaff here in half. So like 1 in 115, right? Which is almost, that's almost like it's almost like a 1% chance. Okay, which is not so bad. Okay. So what's the idea here? So idea is if we have a relatively quick, and we'll talk more about that later, quick way of testing whether a given large integer is prime, we could just pick some odd integer and start testing. What I mean by that is start testing, successive odd integers, right? So pick some large odd 100-digit number, and then just start looking at that number plus, plus 2, plus 4, so on, right? So pick large odd number, and then start testing the sequence of odd numbers right after that follow. Okay. And the point is that if this method of testing is fairly quick, then the fact that this probability that an odd 100-digit number is prime is like 1 in 115 is that it won't take too long to find this 100-digit prime that we're looking for. Okay, like this. Now, a couple things to note. Of course, we've seen that, we believe that factoring a large integer is difficult and would take far too long. So this method of testing had better not rely on fully factoring this thing, because that's no good. Of course, you might say, well, I'm not interested in fully factoring. I really only care about finding a single non-trivial factor, right? But the thing is that in that case, you could just consider, for instance, in one of the previous examples we did, some 100-digit number that is just the product of two very large primes. So even if you don't need to fully factor, just finding one of those fairly large factors is an issue itself. Okay. So that's the idea. Okay, is that hopefully our test that we're talking about doesn't rely on us factoring this in any way. So the first one is actually a result of something that you know well. So Fermat's theorem gives us the first way of doing this. So Fermat's gives us our first primality test. Okay, so Fermat's little theorem says the following. So this is the Fairmont formality test. Fairmont primality test is the following. So let n be an odd integer. So n is the thing being tested. Choose an integer b that is between n and 1. So often we choose b equals 2. Okay, so the smallest possible b. If b to the n minus 1 is not congruent to 1 mod n, well, then what has to be true by Fermat's little theorem? Then n is composite. Okay. So proof. Fermat's little theorem. Okay. Which is the contrapositive of the statement. Okay. So, here's an example. 209 is not prime. So to see that, 2 to the 4 is congruent to 16 mod 209. And now we can do our modular exponentiation trickery by successively squaring this. So 2 to the 8 is 47 squared, which is like, sorry, no, that's 2 to 16. 2 to the 8 is 16 squared, which is congruent to 47. mod 209. And 2 to the 16 is now 47 squared, which is 119 mod 209. And squaring that, so 2 to the 32nd is 119 squared, which it turns out is 158 mod 209. And 2 to the 64 is 158 squared, which is 93 mod 209. And lastly, 2 to the 128 is 93 squared, which is 80 mod 209. And that's the biggest I need, because that's the biggest one. That's the next one will be greater than 209. So, or 208. So 2 to the 208 is congruent to 2 to the 128 times 2 to the 64 times 2 to the 16. 16 plus 64 plus 128 is 208. So yep, that does it. So this is 80 times 93 times 119. And it turns out this is congruent to 36, which is not congruent to 1 mod 209. Okay. Now, of course, 209 is not that big of a number, so maybe if I asked you, without saying anything, show that 209 is prime, what would you do? You'd say, well, I only need to check up to the square root of 209, right? So I only need to check primes up to square root of 209. And then from that, that's not that long of a list of primes. I could just check, whether or not any of those primes up to its square root divide it, right? And then I'm done. But of course, this is just to illustrate how this works. With the aid of computer, this is made an easier check. But obviously, you have a burning question once you see an example like this, which is what happens if you start out with a number, you go through this process, but you find out that 2 to the n minus 1 is congruent to 1 mod n, right? Question is that number definitely prime? Well, no. Okay, there are counterexamples. I'll talk about that in a second. But before I get to that, the thing that I want to draw attention to is note we showed that 209 is not prime without factoring it. And not just without entirely factoring, without finding a single factor, right? So we didn't find a single factor of this thing, yet we showed that it's not prime. Okay, so this is the important thing. I know that 209 is very small, so maybe this isn't that impressive, but this is the impressive bit, that it was able to say whether or not 209 was prime without finding a single factor. Okay. All right, so modular exponentiation, that might seem, this might seem annoying by hand, but of course this is much faster than finding a factor. Okay. Okay. And so, here's another example. So consider, let's see if you can see that. There we go. Okay. So, let's consider using the Fairmont test with b equals 2, and we want to test 10 to the 22nd plus k for k is 1, 3, 7, or 9. Of course, if k is 2, 4, or 8, then it's even. If k is equal 5, it's divisible by 5. So 1, 3, 7, or 9 are our only digits that we care about here, being our last digit. So k is definitely going to be, if k is between 0 and 10, then that's going to determine our last digit here. So if we have the number n is 10 to the 22nd plus k, where k is 1, 3, 7, or 9, then computing, okay, with computer, we calculate 2 to the 10 to the 22nd. That is congruent to this number mod 10 to the 22nd plus 1. And then we compute these successively up to 2 to the 10 to the 22nd plus 8. That is congruent to 1 mod 10 to the 22nd plus 9. Okay. So the thing is that this is composite when k is 1, 2, 3, 4, 5, 6, 7, or 8. But then the suspicion is that 10 to the 22nd plus 9 is prime because of this fact. Okay, but showing that this is prime, our test is not going to be enough to do it, and that's going to take a test called the Pocklington-Lemmer test, which I'll talk about later. Question. What happens if we check for primality of n using some b, but it passes the Fairmont test? Example, if n is 10 to the 22nd plus 9, 2 to the 10 to the 22nd plus 8 is congruent to 1 mod 10 to the 22nd plus 9. Okay. Another example. N is 341, and 2 to the 340 is congruent to 1 mod 341. So, are these then prime? So you might already have guessed or have seen that this one's not. Okay. This was actually the first counterexample, or the lowest counterexample for 2 known. So note 341 is 11 times 31. Okay. Okay. So the answer, no. Okay. But passing this test is uncommon. Now you might have just said, well, we chose a B to test for that n, so why not choose another B and see if it passes? That's a good point. But the thing is that, what if it passes more than one? So what if it passes the test for b equals 2, passes the test for b equals 3, passes the test for b equals 5, and so on, right? Well, The the point here is that it is uncommon, in a sense, and we'll see what that means exactly, for it to pass this test for a single bee. Passing it for multiple bees is even rarer. And so, testing whether or not it passes the Fairmont test for a few of them, typically, if you have a number that passes Fairmont test for a few of them, that is going to strongly indicate that that number is probably prime. But in order to actually say that it's prime, we're going to need a little bit more. So, for instance, as I mentioned, this actually is prime, but the Fairmont test is not going to be enough to get the job done. Okay, it's just going to give us evidence that the thing is probably prime. So this is uncommon enough that we have a special name for it. So definition, a composite integer n greater than 1 is called pseudo-prime, or rather, I should say a B pseudo-prime. If B to the n minus 1 is congruent to 1 mod n, but n, of course, is composite. So if you have a composite integer that passes this Fairmont test for B, this is called a B pseudo-prime. So then, by the example above, 341 is a 2 pseudo-prime. Okay. Another example is 91 is a 3 pseudo-prime. Since 3 to the 90 is congruent to 1 mod 91. But 91's composite. 91 is just 7 times 13. Okay. Okay. But note, we could actually use the Fairmont test to show that these things are composite by swapping the B's, right? So 341 is a 2 pseudoprime, but is it a 3 pseudoprime? Right, the other question, 91 is a 3 pseudoprime, but is it a 2 pseudoprime? So if I compute 3 to the 340, that is congruent to 56 mod 341. And computing whether or not 91 is a 2 pseudoprime, 2 to the 90 is congruent to 64 mod 91. So by the Fairmont test, both are composite. Okay, so this illustrates that even when we have these examples, so 341 is a 2 pseudoprime, but it's not a 3 pseudoprime. 91 is a 3 pseudoprime, but it's not a 2 pseudoprime. That's another way of saying this. Okay. So then there's a question, of course, or a couple questions. So one, if n is composite, is there some b such that b to the n minus 1 is not congruent to 1 mod n? Right? So, question. If n is indeed composite, does there always exist some b such that b to the n minus 1 is not congruent to 1 mod n. So answer, yes. Can just take b to be a prime divisor of n. So if you knew what a prime divisor of n was, then that that will work, since b to the n minus 1 is 0 mod b, right? So it can't be 1. So then additional question. So same question, except I want to get rid of this possibility. So same question, except I require that the GCD of b and n be 1, right? So I require that b and n are relatively prime. Okay. So what is it that we're saying here? We are basically asking whether or not, or we're saying, you know, could you have some composite n that that is a b pseudoprime for a lot of b's, right? That's what is being asked here. Okay, and so here's the idea, right? The idea is that it would be very annoying if you know, there exist a lot of numbers that pass the Fairmont test for a lot of choices of b. So we are hoping that that's not the case, because if that is the case, then this Fairmont test is not going to be that great. So definition. Okay, gives a special name to some of these numbers. So a composite number n is called a Carmichael number. If b to the n minus 1 is congruent to 1 mod n for all integers b relatively prime to n. Okay. Okay. So here's some examples. 561 and 1729 are Carmichael numbers. Someone might recognize 1729 from somewhere, so if you do, let me know in the chat what the significance of 1729 is, or where you might have heard of that, or some property of that thing. So for 561, note that 561 is 3 times 11 times 17. So by Fairmos' little theorem. If b is not congruent to 0 mod 17, then b to the 16 is congruent to 1 mod 17. Right. Thus, b to the 560 is congruent to b to the 16 to the 35, which is 1 to the 35, which is 1, mod 17. Okay. Similarly, if b is not congruent to 0, mod 11 by Fairmont, b to the 10 is congruent to 1 mod 11. Okay, so b to the 560 is congruent to b to the 10 to the 56, which is congruent to 1 to the 56, which is 1 mod 11. Right. Similarly, since b squared is congruent to 1 mod 3, b to the 560 is congruent to 1 mod 3. Right. So, I have some tidying up to do, but these three facts are going to get us there. Okay. Thus, when the GCD of b and 561 is 1, i.e. b to the 560 minus 1 is a multiple of 3, 11, and 17. Okay. Therefore, it is a multiple of 3 times 11 times 17, which is 561. Right. i.e. b to the 560 is congruent to 1 mod 561. Right. And that's for all b such that the GCD of b and 561 is 1. Okay. So 561 is a Carmichael number. Okay. So, was shown, note, it was shown in 1994, so pretty recently. In math, anything in the last 40 years is like mega recent. Okay, that's our that's our metric for how recent something is. So it was shown in 1994 that there are infinitely many Carmichael numbers. But they are relatively rare. Okay. So this, according to computations, there are about 20 million Carmichael numbers less than 10 to the 21st, which seems like a lot, but to give you an idea, roughly 1 in 5 times 10 to the 13 randomly chosen integers up to 10 to the 21st is a Carmichael number. Okay, so these are relatively infrequent. Okay, which is good for our efforts, right? Because a Carmichael number is one that would annoy us when we're trying to use the Fairmont test. Okay, so the nice thing there is an improvement to Fairmont Primality that can often show that Carmichael numbers are not prime. So what this means is that actually there's an improvement on Fairmont primality that, yeah, it's going to take care of this concern that we might have about testing whether or not some integer is prime, and worrying that we end up with some pathological cases that trick us because they work for too many b's. Okay, so this is called strong Fairmont primality test. So, proposition. So this is the strong Fairmont test. So let n be bigger than 1 be an odd integer. Right? N minus 1 as some power of 2 to the k times s, with s odd, so all of the 2's have been extracted. Okay, with odd s and k bigger than or equal to 1. So choose an integer b such that b strictly between 1 and n. Okay, again, often b is equal to 2. Okay, define the following sequence. So b naught is computed to be b to the s mod n, and b sub 1 is defined to be whatever number is congruent to b naught squared mod n, and b sub 2 is defined to be whatever is congruent to b sub 1 squared mod n, and so on, all the way to b sub k, k being this exponent on the 2's here, coming from this factorization of n minus 1. So this is b sub k minus 1 squared mod n. Okay, so then suppose n is prime. This puts some restrictions on how this sequence behaves. Well, if n is prime, then b sub k is congruent to 1 mod n. Okay, and if j is the smallest index for which b sub j is congruent to 1 mod n, then either j equals 0 or b sub j minus 1 is congruent to minus 1 mod n. Thus, if b sub k is not congruent to 1 mod n, or if b sub j minus 1 is not congruent to minus 1 mod n, then n is prime. Or sorry, n is not prime. There. So this is my strong Fairmont test. Okay, so the proof actually doesn't require anything. It's just Fairmont's theorem over again. So this is a very short proof. You can see it on page 326. And a better way of seeing this is just to ask yourself what is being done here, right? So what exactly is being done here, right? And why are you guaranteed that if n is prime, this sequence ends in this 1 in this way? Okay, you'll see what it is that's going on if you have a look at this proof, if you don't see it already from this factorization of n minus 1, right? The idea being that your b to the n minus 1 here is b to the 2 to the k times s. And so what it is that you've done here is you are peeling off, right? Like consider b to the n minus 1 becomes b to the 2 to the k times s. And what you're doing essentially is peeling these apart, right? Okay. So that's where this is coming from. Anyway, this, you should note that just like the Fairmont test, this doesn't prove primality. It merely gives you some evidence. Okay, so it can only be used to show that a number is composite, not that a number is prime. But this gives you some evidence. So here's an example. Maybe I don't have enough room to start here. So if n is 41 and b is 2, then n minus 1 is 40, which I can write as 2 cubed times 8. Or sorry, 2 cubed times 5. 2 cubed is 8. So s is equal to 5 and k is equal to 3. So then I compute b naught is congruent to b to the s, that's 2 to the 5. So that's 32. Right, and we're doing this mod 41. I won't write it other than that. So b sub 1 is 32 squared, which is 40 mod 41. B sub 2 is 40 squared, which is 1, because 40 is minus 1 mod 41, so this is minus 1 squared, so that's just 1. And then b cubed is, of course, 1 squared. Or sorry, b cubed, it's not b cubed, it's b sub 3. This is 1 squared, which is also 1 mod 41. So b sub k is b sub 3, which is 1. Okay, smallest j with b sub j congruent to 1 is j equals 2. Then b sub j minus 1, which is b sub 1, is congruent to 40, which is congruent to minus 1 mod 41. All right, which I noted previously. So 41 is probably prime. Right. Note, we can't say for sure with this test alone. So with this test alone, it's not enough to prove that it's prime. It's just to give us evidence that it is probably prime. Okay, because passing the strong Fairmont test is harder. Another example is if n is 91, b is 3. So then 90 is 2 to the first times 45. Right, so S is equal to 45 and K is equal to 1. And B naught is 3 to the 45, which is 27 mod 91. And B sub 1 is 27 squared, which is 1 mod 91. Right. So B sub 1 is equal to 1, but B sub j minus 1, with j being the smallest integer for which is the case, which is 1, is B naught, which is not congruent to minus 1 mod 91. Thus, by strong Fairmont test, 91 is not prime. Okay. So, the reason I wanted to show you this example is because we saw earlier that 91 is a 3 pseudoprime. Okay, and so the important bit to get out of this example is that if we had chosen B to be 3 and N to be 91 for the usual Fairmont test, well, 91 is a 3 pseudoprime, so we would have gotten that B to the 90 is congruent to 1 mod 91, and we'd say, oh, well, okay, 91 is at least a 3 pseudoprime, so I would have to check another base. But here, even though in the strong Fairmont test we picked the same base for which the number was a pseudoprime, the strong Fairmont test sniffed out that this actually is a composite number. Okay, so this can pick up things that the normal Fairmont test won't. Okay, so actually, the strong Fairmont test lets very, very few composites slip through. And it turns out, I'm not going to go over this, but in the I will, but I'm not going to prove these statements. I'm just going to list them. But basically, it's if a B pseudoprime fails the strong Fairmont test, it can be easily factored. So this is special enough to still give a name to. So definition: a composite integer n greater than 1 that passes the strong Fairmont test for B is called a strong B pseudoprime. Okay. Okay. So these are very rare. All right. So, to give you an idea, in fact, so that I'm not just reading into the void here, here is a nice description of what's going on. So the strong pseudoprimes are rare. It says if you look at the integers less than 10 to the 8, 488 of them are strong 2 pseudoprimes. 582 are strong 3 pseudoprimes, and 475 are strong 5 pseudoprimes. And of the 488 strong 2 pseudoprimes, only 21 are also strong 3 pseudoprimes. And of these, there is only one strong 5 pseudoprime, which is this number, 25,326,001. Okay. So you can actually check, once you see that it's not a strong 7 pseudoprime. So of all the integers less than 10 to the 8, there's not a single one that is simultaneously a strong 2, 3, 5, and 7 pseudoprime. Okay. And so this nice fact is listed here. So in fact, computations of Pomerantz, Selfridge, and Wagstaff show that if n is less than 25 times 10 to the 9 and it's composite, it cannot be a strong pseudoprime for all 5 of 2, 3, 5, 7, and 11. So then that leads to a simple primality test. So given an integer of that size, check that it passes the strong Fairmont test for 2, 3, 5, 7, and 11. If so, then it is guaranteed to be prime. Okay, so knowing these additional computations, we actually can have a direct primality test that if it passes strong Fairmont tests for b equals 2, 3, 5, 7, and 11, then it has to be prime. Okay, so here is, I'm not going to actually write this out. This is an example of a probabilistic primality test using the strong Fairmont test. So basically, so in practice, if n is composite, it's easy to find a b such that n is not a strong b pseudoprime. So this was shown under the assumption of the generalized Riemann hypothesis that if n is composite, then there is a b less than 2 times the natural log of n squared, such that n is not a strong b pseudoprime. Okay, and then this was later shown that there are at least 3 times n minus 1 over 4 values of b less than n, such that n is not a strong b pseudoprime, which leads to the following probabilistic primality test known as the Miller-Rabin primality test. So test n using m randomly chosen values of b less than n. Okay, if n is composite, the probability that it is a strong pseudoprime for 1b is at most 1/4. So the probability that it passes all m tests, right, is 1 over 4 to the m, right? You just multiply 1/4 m times. And therefore, if it passes all m tests, then n is prime with probability at least 1 minus 1 over 4 to the m. So you see how this quickly, if it passes just a handful of these, it is very likely to be prime. Okay, which is where we get this notion of probably prime. Okay, so because the strong Fairmont test is pretty quick, this is actually a pretty good method for choosing these cryptographic primes. Okay, so this is a nice fact, right? And this ties together a lot of ideas where there I could compute, I could prove some probabilistic statement about, what is the probability that some given integer that passes, so many strong Fairmont tests is prime. This just gives me a good idea of where I could focus my efforts if I really, really need to show that something is prime, but I'm just not sure, right? So what do I do in that case? So here's my first example of a primality test that can actually say whether or not the number is prime. So the Fairmont tests can show when a number is composite, and passing multiple strong Fairmont tests especially increases the likelihood that the thing you're dealing with is prime, but can't directly say, without some additional info, can't directly say that the thing itself is prime. So suppose n passes the strong Fairmont test for several b, so for several values of b, so I suspect that it is prime. How do I actually prove that it's prime? Okay. Well, I can try to partially factor n minus 1. If I suspect n is prime, then n minus 1 is even, so at least it has a factor of 2. So I can begin my process there, right? The idea is to try to partially factor n minus 1. Now, in the event that we can't do this, in terms of the methods that we're going to talk about in this course, we're kind of sort of screwed, because if I want to use any kind of more sophisticated method, then it would take a lot more effort to go into that. But in the event that we can partially factor this n minus 1 satisfactorily, then we're in good shape. So the idea is called the Pocklington-Lamer test. Okay, so let n minus 1 be partially factored as big F times big N. Okay, where big F and big N are relatively prime. Okay, the way to remember this is F is factored and big N is not necessarily factored. That's what the big F and big N stand for. So suppose there exists B such that B to the n minus 1 is congruent to 1 mod n, and the GCD of B to the n minus 1 over Q minus 1 and n is equal to 1 for all primes Q dividing F, then each prime factor P of little n satisfies little p is congruent to 1 mod big F. And if big F is greater than big N, then N is prime. Okay. Okay, the proof of this is not too bad. This is on page 329. So this uses some facts about congruences in order and the order theorem that we're well familiar with by now. So yeah, this is on page 329. What does this say exactly? So I need to be able to factor n minus 1 enough that I get it satisfying these hypotheses and with big F strictly larger than big N. If I can do that, then this little n that I'm trying to show as prime is in fact prime. Okay. So how does this work? So here's an example. So let's use Pocklington-Lemmer to show that n, which is 9,473, is prime. Okay, so we can factor 9,472 as we can pull 8 copies of 2 out of it, so that makes the job easy, times 37. Okay. All right. So we take big F to be 2 to the 8, which is 256. Big N, of course, 37. Okay. We compute 2 to the n minus 1 over 2, which is congruent to 1 mod n. Now, what are we doing here? We are trying we're trying a b equals 2 here, so that every prime dividing f, in this case the only prime dividing f is 2, just 2 to the n minus 1 over q, so for us it's 2 to the n minus 1 over 2. We're checking what this is congruent to, mod n, right? And so note that this is actually so 2 to the n minus 1 over 2 is congruent to 1 mod n, so b equals 2 does not satisfy the hypothesis of Pocklington-Lemmer. So we can't use it. Which hypothesis is that? So this is, there are 2 requirements. Here and here, right? Okay. So it doesn't satisfy the second requirement, that this GCD between b to the n minus 1 over q minus 1 and n are both 1 for all primes q dividing big F. Okay, so that's b equals 2 doesn't work, but b I shouldn't write it as b, but 3 to the n minus 1 is congruent to 1 mod n, and 3 to the n minus 1 over 2 is congruent to minus 1 mod n. So the GCD of 3 to the n minus 1 over 2 minus 1 and n is the GCD of this 3 to the n minus 1 over 2 minus 1 is congruent to minus 2 mod n, so this is minus 2 n, but this is 1. Thus, b equals 3 satisfies the hypothesis in Pocklington-Lemmer, and so 2 is the only prime dividing big F. And big F is bigger than big N. Big F is 256, and big N is 37. So little n, which is 9,473, is prime. Okay. So that's one way of doing it. Okay, so here's another example. So let's show that little n, which is 10 to the 22nd plus 9, is prime. So this is a much larger prime than we've ever shown is prime, I think. All right. And so, what do we do here? Well, first we factor n minus 1. So n minus 1 can be factored as 2 cubed times 3 squared times 17 times 8747 times 11,161 times a number that is large. I'm just going to read off the digits from left to right. So this is 836, 866, 81651. Okay. So this is going to be my big F, and this is going to be my big N. Okay. So what is the point here? You might say, well, my God, if I can do this, then you know, what's my issue? The thing is that factoring in minus 1 is a little different than factoring in. Some of these are going to be easier to factor than others. You know, being able to factor n minus 1, if you can't figure out a way to do this, then as I said before, you are basically stuck, and you would need more complicated methods. But it turns out that for the primes that you might be interested in testing, a lot of these n minus 1s are going to be eminently factorable. So this is not so bad. Okay, yes, more complicated, like more sophisticated methods are needed if you can't do this, but this is going to work for a nice amount of potential primes, right, that you suspect are primes. So here's my big F, here's my big N, and so you can show that 7 to the n minus 1 is congruent to 1 mod little n, and the GCD of 7 to the n minus 1 over q minus 1 and n is 1 for q, that is 2, 3, 17, 8747, and 11,161. Thus, PL hypotheses are satisfied, and big F is strictly bigger than big N. So 10 to the 22nd plus 9 is prime. Okay. Okay. So this gets you fairly large primes in this way, but again, as I said, there's limitations here, and I mean, you can't expect too much in a sense because when it comes to primality testing, if it was extremely easy, right, then that might give you some worry about any kind of encryption methods that rely on factorization being hard or on these computations involving primes being hard. If this were a lot more doable, then there would almost certainly be some underlying issue. So there's a couple of other examples of primality tests that I was going to mention, and I might mention them before starting to talk about chapter 15. The subsection 14.2.3 talks about Aks Primality Test. So this is a fairly new one. This is from 2002. This is a good it's a good example of a very good primality test. It's not fast enough at the moment to be better than what are the current best state-of-the-art primality tests, but it has some advantages, and yeah, so that's all I guess I'll say about it for now. But it should be noted that when you are dealing with special types of primes, i.e. Fairmont numbers or Mercen numbers, so numbers of special forms have special primality tests that are faster than general tests. Okay. So for Fairmont numbers, so remember, Fairmont numbers look like this. So they're 2 to the 2n plus 1. So there's Papan's test. Which says, so let n be greater than or equal to 1. F sub n is prime if and only if 3 to the f sub n minus 1 over 2 is congruent to minus 1 mod f sub n. Okay. So I believe this was originally shown using 5 in the place of the 3, but then it was shown later that 3 works just fine here. And for Mercen numbers, so the Fairmont numbers are, the conjecture is that none of them pass f sub 5 so none of them pass the first 4. So starting at f sub 5, they're all composite, right? That's the conjecture. And for Mercen numbers, the fast test is called the Lucas-Lammer test. So remember, Mercen numbers, this is m sub p, which is 2 to the p minus 1. And Lucas-Lammer says let p be prime. Define a sequence by S naught is 4, S sub I plus 1 is S sub I squared minus 2. That's an S sub I. I don't know what I'm doing there. Okay. Then m sub p is prime if and only if S sub p minus 2 is congruent to 0 mod m sub p. Okay. So the proof of Papan's test is on page, so this proof is on page 334. And can be done with, is actually by Pocklington-Lemmer is one way to prove this. The proof of this test for the Mercen numbers would require more stuff. It's actually proven in chapter 19 of the textbook, but it would require a little bit more stuff. So one thing I'll say here is that, of course, it is to be expected, right? It's not that surprising that when you're testing numbers that have a very specific form, there's very specific tests that you can apply to those numbers that are probably going to be faster than pretty much anything you're going to come up with. So because a test, right, that's designed to test general n, of course, has to be a little bit more. It has to be a little bit more tolerant, whereas these tests are more narrow and focused and make use of the fact that the numbers you're dealing with are of a very specific form. As I mentioned earlier in the semester, the current largest primes known are Mercen, is a Mercen prime. And I believe this is primarily the test that's used. So the Great Internet Mercen Prime search, so GIMPS, uses this test to test the primality of Mercen numbers. So as I said, I believe something like the last 17 of the Mercen primes that have been found via this online project. And as I said, I believe this is the test that's actually used. Yeah, it says here in the textbook, Great Internet Mercen Prime Search uses the Lucas-Lammer test to search for very large Mercen primes. So this is good enough to be able to search for ultimately the primes that are the largest currently known prime numbers. Okay. So anyway, that is to give you an idea of what you might do, something you might do if you needed to show that some given huge number was prime, right? Maybe, or even if you needed to come up with some very large prime for cryptographic purposes, how would you do that? The idea is by prime number theorem, distribution of the primes tells you that they're not so rare that if you were to just search for odd integers starting at some large 100-digit number and you had a relatively quick primality test for those, you could basically just start at 1 and run them for the subsequent odd integers until you find one that is prime, and then you can use that for your purposes. Okay, so anyway, tomorrow I will start on chapter 15. And after we finish what I'm going to talk about in chapter 15, that is the core bit of the course that I absolutely wanted to get to. And past that, Like I said, I may do some examples of elliptic curve stuff. I may venture, if I think that time would be more efficiently spent elsewhere, I may venture into some other topics. But that's more or less the course. So today I'm having office hours at 2, so I will post a reminder about those when they happen. But other than that, I will see you all later today, hopefully. Oh, questions. Oh, I see. I see. Is AKS complexity polynomial? It is. It is polynomial. So it is polynomial, but so the thing is that and uh, while some of these better tests are actually uh, slightly slower than polynomial time, practically they are faster than AKS. Yeah, and I'll put that in the chat just for people watching later, so that they'll see my answer and don't have to actually listen to this last 30 seconds. So I'll put that into chat here in a second.